Welcome back to discussion 27, where we talk about sound and sound waves. We're going to start looking at problem 29 on page 518. Okay, so we're given some information right away. The smallest amplitude detectable by your ear is 1 times 10 to the negative 11 meters. So that's the actual amplitude of the wave that you can detect, right? So now we're saying if we have a frequency of 1,000 hertz, what is the smallest pressure amplitude that you can hear under the ocean? So we're looking for the pressure, right? So if we can hear this, if we can detect this amplitude, what's the pressure amplitude that we can hear in the ocean? And then it says, see, there's an example 17.4 in the book, and they kind of do a very similar thing here. So I recommend going through that. It's worth looking at before you approach this problem. So in the example, they give us, there's also a derivation for this in the book near the example, times S max, where this is the largest amplitude you could hear. This is the speed of sound in air. This was the density of air, and this was the angular frequency of the oscillation of the wave, right? And so now what we need to do is we actually have to look up, so their problem was they wanted to find this in air, right? Well, we're not looking for this in air, we're looking for this in seawater. So we need the density of seawater. Well, if you look that up, you end up with a value of 1,025 kilograms per cubic meter. So it's much more dense, which, right, obviously, we know that. Okay, so now we're given a frequency, and we have a relationship between angular frequency and frequency. What is that relationship? That is going to be, it's going to be 2 pi f is equal to omega. So then we just multiply this value by 2 pi, and we get what we're looking for. So let's go here. So then omega is equal to 2 pi times 1,000. Okay, and then S min, we were told, is 1 times 10 to the negative 11 meters. So do we have everything that we can plug in? We're given the speed of sound in seawater. We have this. We have S min. Remember, we're looking for the minimum. We have this. Okay, we have everything we need. So let's plug this in. So let's just replace this max with a min because it's the same relationship. So we have 1025 cubic meters times the angular frequency. Remember, this is 1 over seconds. And that's going to be times the speed of sound, which was 1531 meters per second. And then times 1 times 10 to the negative 11 meters. Really? And then so you just plug this in, and then you get a value of 0.0986 kilograms meters second squared. This is also units of a Pascal. So we could say this is roughly 0.1 Pascal. Right, so okay, so what we can do here is we can take, we're asked to find the ratio. So we want to take P min It doesn't explicitly ask us to take the ratio, but it does ask us to compare the two values. And so oftentimes it's better to just take the ratio, and then you can see what kind of percent difference you get. So I'm going to say that this is 0.0, well, let's do this, 9.9 times 10 to the negative 2, right? 9.9. That makes sense. I rounded up quite a bit here, but let's keep it closer to the original value for this. And then the one in the problem, they ended up with 3 times 10 to the negative 5. So this gives us a value 3.3. So this is negative 2 minus negative 5. So this is going to be times 10 to the 3. So this is going to be, so now what we're being shown here is that the pressure, the minimum pressure in ocean water is 3.3 times 10 to the 3 times louder than in air. I guess I should actually say higher, not louder. So we're talking about a change in pressure. But either way. Okay, next problem. Number 37. We're given a rope with tension. So we're given that the rope is 5 meters long, it's 0.65 kilograms. The amount of power supplied to the rope is 1 kilowatt. We're given a wavelength, we're given a wave speed, and we're asked to find y max. So I'm not totally sure. Let's see. Okay, we're not going to necessarily need this, maybe, but we can figure this out. So we're given Vx, and we're told that the rope is under tension. We have a tension force, and then we're also told the mass over the length. So that actually gives us a linear density. So what that means is that we can actually use this relationship to find the tension force. So the tension force, if you remember from the problem we did last time, was equal to Vx squared times linear density. And so now we have V is this speed, and the linear density is going to be your mass over your length, right? So that's going to be 0.65 over 5. And this is kilograms per meter. And you plug all this in, and you end up with a value of 325 newtons. So I'm not sure if we need that for this problem, but that is useful. You might encounter a problem where you're asked to find that. So we're told that the power that is supplied to the rope as well. The power is 1 kilowatt, right? So what we can do is we need to find our equations for intensity and power, because those are related. So here we have an intensity. We have pressure difference, and over density times the speed. Where the difference in pressure is equal to something we just looked at, right, times the amplitude. So this in general is what we're looking for. We're given power. We also have a relationship between average power and y max. So we could just go for something like this, right? This is also something that we can find pretty readily available in the book. So I was just listing equations that we might be able to use, and it looks like this one is the most straightforward. So let's see, what are we given here? We're given, remember we were able to find a mass density, mu, so that's fine. We were given the speed, which is this. We were also given the power. And what about angular frequency? Is that something that we can find? Well, I believe it is. Let's just look at a couple of relationships that we have, again, for angular frequency. So remember that the speed is equal to angular frequency over k. What is k? K is equal to 2 pi over lambda. Are we given a lambda? We are. So look, we can plug that in. So k is equal to 2 pi. What was our lambda again? It was pi over 4. Right, so pi over 4. So these cancel. This is 8. 1 over meters. Okay, so I mean, then we can say omega is equal to, what is it? It's 50 meters per second. Right, so all I'm doing here, let me be more explicit. So all I'm doing here is I'm just solving for, I'm taking this to the other side and solving for omega. So omega is equal to k times v sub x, and that's going to be equal to 8, 1 over meters times 50 meters per second. These units cancel. So that gives you a value of 400 radians per second. So then we just plug that in, right? So we can just use this equation. So we don't need these other ones. These can take off. We don't need those. We only need this one. So let's just plug in to this equation. So the power was 1,000 watts. So let's just write that out. 1,000 watts. It's going to equal half times, what was it? It was 0.65 kilograms over 5 meters times 400 radians per second squared. I mean, all squared, right? And this is y squared max, which is what we're trying to solve for, times 50 meters per second. So we just solve for y max. That's going to equal let's do this. 2 times that times 5 over 0.65 times 1 over 400 second squared. This is going to be 1 over 50 seconds per meter, and this is all under a square root. So you plug all this in, and then we get a value. Let me just double check my work here. This is 1 over 400. Oops, this, see, that's wrong. So this is squared. That's, now we're right. Now we're good. And this gives you a value of 4.4 centimeters. That's what I got. I mean, more explicitly, we got 0.0438 meters, and then that becomes around 4.4 centimeters. Okay, so that's your answer. So next problem, number 39. Number 39, we're given a wavelength, a speed, average power, density, and we're asked to find the energy. This is problem 39, right? And so this is the sound. I mean, all of these waves are sounds. So these are all sound waves. So I'm not sure if I was clear about that earlier, but I'm going to make sure that that's what we're taking care of. So we're told that a sound with a wavelength is produced in air, and it travels at the propagation speed of 343 meters per second. That's your average speed of sound in air, right? The average power of the sound wave is 40 watts, and if the density of the air is what we're given here, 1.2 kilograms per meters cubed, what is the energy contained in one wavelength of the wave? So we just want to know what the average, or what the energy is in one wavelength. All right. So first thing we need to do is revisit energy. So if we look at the energy transport in a wave, we have this, we have a relationship, right? Okay, let's look at kinetic energy. Recall that we actually found the total energy for our oscillating pendulum was this, right? And that's going to give you something like this, where R would be your maximum. Okay, and then instead of considering mass in this situation, we can consider density and wavelength, right? So mass per length is going to give you some linear density. So that means that energy net is going to equal 1/2. Take this over here. It's going to give you linear density times wavelength times y max squared times angular frequency squared. I feel like this is something we can probably use. Okay, we're given the density. Okay, here. We also have one more relationship that we need to look at, because also we're given power, right? This is something that we actually know as well. We just used this in another problem. So something like this. Y max squared times the speed of the sound. So we want to know, we're actually looking for the energy in this problem. We're looking for the energy contained in one wavelength of the wave. So since we want energy, this is still valid. What we can do is, these are all of this is in terms of things that we know, so we can solve for y max in terms of the things that we know and plug that into this equation. So what does that give us? Well, that gives us power times 2. This is something that we did earlier. Right, remember that this is in a square root, but now we actually want it squared because it's squared in this equation, so we may as well just leave it squared, and that's fine. So now we have energy net is equal to 1/2 mu lambda 2 times the power average times 1 over mu omega squared Vx, right? Times, what do I have? That's times omega squared. So those cancel. The density cancels. The 2's cancel. And then we're left with just the average power times lambda, the wavelength, over the speed of the wave. And this is all in terms of something that we definitely know, right? So we have 659 meters. This is 343 meters per second. So those cancel, seconds go on top, right? Average power was 40 watts. So we multiply these values together and we end up with a value of 0.768. Now let's just check our units to make sure everything is okay. So watts is actually joules per second. That's going to be equal to a Newton meter per second, which is equal to kilograms meters squared per second cubed times seconds, right? Because this second down here went up on top. So that gives us second squared, which is equal to kilograms meters squared per second squared is a joule. So we're in joules and we're good. So that's the value. I'm not sure if I mentioned this also, these relationships and this derivation can also be found around page 500. So if you want to have a more in-depth look of these concepts, that's where you can find it. Okay, number 69, we're told if the intensity of a sound wave increases by 1%, what is the change in the sound level of the wave? What is the change in the sound level? Well, in the book we're also given this relationship, 10 log, this is log base 10 of your intensity over an initial intensity, which is actually a given value, so this is actually equal to I over 10 to the negative 12 watts per meters squared, right? So this is your sound level. So this is also where this is a unit of decibels. Okay. So we're looking for a change. So what is the change in the sound level? So what we're looking for, change in the sound level, is going to be delta beta, right? So that's going to be some beta final minus beta initial, I would say. Okay. So that's a pretty good start. And now we're looking for a 1% increase. So typically when we're looking at percentage differences, we go something like this, right? And then we multiply it times 100 and we get a percent, right? Well, in this case, we're not looking for the decrease, we're looking for an increase. So we're going to actually have this, and this is equal to 0.01, because this is 1%, right? So if you multiply all this by 100, you get your percentage. So that means that we have our ratio. Sorry, I should be more explicit in that I am considering I prime is the new value. Okay, so this is like the increased intensity over the old intensity. So now we have this is equal to 1.01. So that's important. We're going to need to know that. And I'll show you why. Okay, so delta beta is equal to 10 log. So the final intensity, right? We're looking for the final intensity. That's going to be I prime over I naught minus the initial sound level is we're just calling it I over I naught. Using properties of logs, we can get something like this. Let's just do this log. So when you have, just a quick review, when you have log x minus log y, you end up with log x over y, right? So that gives you then 10 log I prime over I naught times the inverse of this argument. I naught over I. Okay, well, these cancel. Then we're just left with 10 log I prime over I, which from the relationship that we just found is equal to 1.01. So let's plug that in. 10 log 1.01. That gives you 0.043 decibels. That's the change, right? So the intensity of the sound wave increased by 1%, and we had a change in sound level of 0.043 decibels. Okay, so the next problem, we're told sound waves are leaving a speaker with a total energy of 275 joules in 4 seconds to a location where the energy of the sound waves is spread over an area of 5 square meters. So we're told, okay, let's write down a few things. We're told what? Total energy is equal to 275 joules. The time in which that happens is 4 seconds. We're also told that the area is 5 square meters. Now we're asked, what is the intensity of the sound at this location? So we're asked for intensity, and intensity is watts per meter squared. So it's power over an area, right? So what we would need then is we would need power, average power over area. And so to find average power, we can take the total energy output over the period, right? Over the change in time. So the total energy output over the total time period. This gives us a value .75. This was, what was, oh, this is power, so that's watts, right? Joules over seconds. So then we plug this in. We take 68.75 watts over the area that we are affecting, and that gives us a value of 13.75 watts per meter squared. So that answers the intensity of the sound at that location. And then we're also told we want to know what is the sound level at this location, right? So we know the intensity, it's this. And remember from the last problem that we had a relationship that looks something like this, right? So then we just plug this into here, and we end up with 131 decibels. That's the sound level. Okay, and then we have to do the same thing. We have to do the same thing for 20 square meters. So this is the area that we're affecting now. So we just plug the stuff in, right? So we have 68.75 watts over 20 square meters. That gives us a value of 3.44 watts per meter squared. And then for the next part, we just plug that in to find the sound level. 3.44 over 10 to the negative 12 gives you a value of 125.4 decibels. So notice that we're talking about an area of 5 square meters. The sound level was pretty high, and then when we go over to 20 square meters, it goes down a little bit. Also, I'd like to point out that these levels, these sound levels, are extremely high. I mean, like, not like, they're not so high that it's unrealistic. You can get sounds like this from like jet engines and stuff. But you would definitely hurt your hearing if you were exposed to those sounds. You might even go deaf. So moral of that story is wear hearing protection if you're exposed to sounds at these levels. 80 decibels is reasonable. And for maybe, 20 to 45 minutes. But more like 20 minutes. 60 decibels is around like an average, is like an average sound level, and that's, you can just be listening to 60 for any time, for any amount of time. Anyway, that's the answer.